Okay, hello everyone. I am Jinghuan from City University of Hong Kong, and I'm presenting our paper Adoc, automatically harmonizing data flow between components in log structure key value stores for improved performance. And this is the outline of the presentation. Let me start with a quick introduction on the background of LSM-KV and the red store problem. So today, LSM-KV is quite a popular system and has been widely used in many different scenarios, like KV store clusters, DB engines, log storage servers, and blockchain storage. And in this paper, we choose the RocksDB as the starting platform, since it's the most popular and representative one. So a typical LSM-KV system consists of three major components: the memory component, which buffers the newest changes in the active mem table; the commit log, which saves the operation records and ensures system consistency; the disk component, which stores the persistent data in SS tables and organizes them into multiple levels. There are two major operations working in the background of an LSM-KV system. The first is the flush, which transforms the immutable mem table into level 0 SS tables. And since these level 0 SS tables are directly flushed, this level is different from other levels, which is unsorted and overlapped. And the second job is the compaction, which merges and sorts SS tables from shallow levels to the deeper levels. So level 0, level 1 compaction is also different from other compaction jobs, as it will collect all the level 0 SSTs as the input. Therefore, the processing of level 0 is critical to the system performance. Okay, red store is a common problem noticed by many priori studies, which behaves as the sudden performance drop in the system performance. And in this paper, we are going to observe how the red store problem reflects on all devices. As shown in this figure, the x-axis is the time elapsed, and the blue lines show the real-time throughput. And we can see that red store is universal, as it occurs on all kinds of devices. And the store pattern can be very different from each other, shows the red store problem is highly device dependent. And since this paper is based on many experimental observations, we list the setups at here. In this paper, we are trying to find the universal cause of red stores, which may suit for all types of the storage devices. And after finding the reason, we are trying to find a solution based on this universal explanation. So let's first start with a quick reviewing on the former studies. So there are many priori studies trying to explain the formation of red stores. And the conclusions they made can be categorized into these following three types. But for each category, we observe some opposite situations. So here we have three figures. So priori studies first conclude the cause of red stores as the resource exhaustions, which means the red store is either caused by the shortage in CPU utilization or the shortage in the disk bandwidth. However, our observation shows that this is partially true. Take the NVMe SSD as an example, as shown here. So after increasing the number of threads in the axis, the red store still occurs, which behaves as the dotted lines in the right y-axis. And store duration still there, means there's red stores occurring. However, we observe an obviously decreasing CPU utilization at here. And there are huge gaps between the average bandwidth and peak bandwidth and the theoretical values of NVMe SSD. So priori studies also think the execution of level 0, level 1 compaction is the cause of red stores, as they observe the occurrence of red stores behaved as the performance drop aligns the execution of level 0, level 1 compaction, as shown by the left arrows in figure A. However, this is still partially true, as the alignment soon disappears after rounding for a while. And in figure B, where there are sufficient number of threads to run the compactions, the execution of level 0, level 1 compaction and the performance drop never matches from the beginning. Okay, for There are also priori studies notice that write stores always occur when there are too many compaction jobs in the background, which may lead to severe resource competition. The x-axis here shows the number of threads, and the y-axis here shows the occurrence or the occurrence frequency of the background jobs. We noticed that the number of deep-level compactions still increased until the number of threads reached 8, while the store occurrences decreases from maybe when it exceeds 6. Okay. In this paper, we propose a new concept to explain the formation of write stores, which can also explain the unexplained facts we mentioned. In an ideal case, the data flows follow a harmonious manner. However, when the balance gets broken, harmony collapsed and occurs write stores. So it's similar to the concept of disk overflowing has been mentioned by many priori studies, which is referred to the background I/O spikes, and these I/O spikes block the system input. However, data overflow is more than that, as it considers the overall harmony between all components. According to the components, we categorize the data overflow into 3 different types. Let me explain the definition of the data overflow first. It refers to the case that the input rate of one or more components is higher than the output rate, while this output rate is determined by the processing rate of related data movement jobs. As the consequence, the related components will expand rapidly, and this will cause the write stores when it exceeds the size threshold defined by the system. In detail, when the flush is slower than the system input, it forms memory overflow, and the system will be stored when there is no room for the new input. And when level 0, level 1 compaction cannot remove the SS tables in time, level 0 overflow occurs. And as shown here, the size of level 0 keeps growing, which is the y-axis of the black lines. And the system will be stored when it exceeds the limitation, which marks by the blue lines here. When the compaction rate in deep level cannot match the generation rate of the SS tables, redundancy overflow occurs. As shown in the figure, redundancy overflow occurs, as shown in this figure, we can see the redundant data, the redundant data size, which is the pending input for the compaction jobs. This redundant data size keeps increasing, and when it exceeds a limitation, it causes PS store, which we call the pending size of input store. After introducing the data overflow concept, we will explain the unexplained points in the former sections. So remember the occurrence of write stores when resources are idling. Memory overflow explains what is happening. So after increasing the number of threads, the flush rate is decreased, as shown by the arrows here. This forms memory overflow and leads to more frequent mem table stores. The total input data is limited, and so does the scheduling and execution frequency of the background jobs. As a result, the CPU and the disk will remain idle, and it will keep decreasing after crossing the tuning point. After crossing the tuning point. Then it's the misalignment between level 0, level 1 compaction and the performance drop, which is shown here. In figure A, when there's only one thread to run all the compaction jobs, level 0, level 1 compaction will be waiting in queue, and this will reduce the average processing rate of level 0, level 1 compaction in disguise. Level 0 overflows occur and forms write stores before level 0, level 1 compaction gets executed, and system performance will recover after the compaction has removed the files. So in figure B, when there are enough number of threads, to run all the compaction jobs in time, the performance drop here is much more regular and with shorter duration, since it's mainly influenced by the memory overflow and the mem table stores. I may skip these slides due to the time limitation, and if you are interested in the explanation for the crowded compaction jobs, please refer to the paper. I will go through it quickly. So we can find that the increasing number of threads will reduce the system input, lower down the requirement of compaction jobs, cause less level 0 overflow, redundancy overflow, and since these two overflow duration shorter than the memory overflow, the total store duration is decreased. So we have the answer for the first question, that data overflow is the universal cause of write stores. And here we propose the Adoc tuning framework to remove or even alleviate the write stores. So in this section, we will introduce the design of Adoc, compare the design advantages with the SOTA work, and show the performance improvements. As shown in this figure, the black blocks present the original store detection of RocksDB, while the red blocks show the extended steps of Adoc. So Adoc tunes the number of threads to adjust the flash rate and background parallelism, and tunes the batch size, which is the common size of mem table and SS table, to control the scheduling frequency. The tuning algorithm is based on the AMD algorithm, which is widely used in the TCP congestion avoidance. Here we present two tuning framework. The first is Sook, is the state-of-the-art work. However, it needs manual optimizations to find a suitable startup configuration, and it could be hard to transplant. And Adoc does solve this weakness. It's fully automatically, it's easy to update, and it can be deployed with other tuners. So just as we mentioned, Sook needs some manual optimization. So there are two schemes. It's named Sook P and Sook O, refer to the configuration used in the paper and manually optimized, respectively. So there are many experiments results shown in the paper. We have to pick the most important ones to present here. Please refer to the paper if you are interested. So this figure compares the throughput of fair random workload, and y-axis means the red lines means the average throughput, real-time throughput. The black line here, the black dot line here means the average throughput, and we can see that Adoc achieves much higher average throughput and much higher peak throughput than the SOTA work, because it will tune on all write stores, and it won't limit the bandwidth of the background compaction jobs. In this figure, we compare the store duration and different kind of write stores. So we can see here, the Adoc shows significantly store reduction on all devices, on all devices, which is shown by the bars here. But we found the occurrence of pending byte input store is slightly increased, which is shown by the blue lines here. This is because Adoc has much higher throughput than the Sook, and it accepts more input data, which is shown in here, and it will cause more it will cause more compactions, and it will slightly increase the PS store. So in the end, we present the performance of Adoc in YCSB workloads, since the write pressure in YCSB is lower than those in the fair random workload. Adoc performs worse because it has less opportunity to tune the system. When compared with the manually optimized Sook, Adoc can be slower, especially in the read-dominate operations, since the Sook O here, optimized Sook, use a much larger mem table at first. So here comes the conclusion. We propose the concept of data overflow, which explains the write store shown in all types of devices. And then we proposed an auto-tuning framework named Adoc to remove, avoid, and even alleviate the write stores. And that's all for my presentation. Thank you, and any questions?
Let's first thank the speaker.